There we go. Okay, so starting the new unit on related rates, the first thing I've done is I've just listed some basic steps for solving related rates. Everyone, you need to write these down and you need to follow these steps. A lot of these kind of will feel like the steps for solving any general word problem, right? Whenever you're solving a general word problem, you always write down what you're given. You always write what you're trying to find. You should, right? Sometimes you draw a picture, right? It's not a requirement, but it is helpful. Same thing with related rates problems. Sometimes drawing a picture is helpful. You don't have to, it's certainly not required. A lot of times they give you the picture, right? But it can be helpful. But these are required. And when you are taking your AP exam, if there is a free response related rates question, and they come up every so often, not every year, maybe once every few years, right? You'll see a related rates question pop up in the free response. They give points. They are going to look for this, and they will give you a point for writing what's given. They might not give you a point for that, but they usually will give you a point for this. So they'll usually give at least a point for writing what's given. And then they will definitely give you a point for writing an equation that relates to variables, right? Then they're going to for sure give you a point for differentiating, right? And then a point for your solution. So make sure when you're doing these problems, don't skip these steps. These are important. They are worth points, all right? So you always want to start by writing what you're given and what you're trying to find. The next thing you want to do is you're going to write an equation that relates the variables. A lot of the equations today are going to be with geometry. Not all, but many. There's a lot of geometry in related rates. Go ahead. All right. So that's okay, and we'll do a quick review of what geometry formulas you are going to have to memorize, and which ones you won't have to memorize. All right. Typically, three-dimensional geometry, for the most part, the formulas are given. But two-dimensional, you'll have to know. So, area of a circle, square, triangle, right? You should know those. But if they ask you like volume of a cone, they'd give it to you. All right. So you write an equation that relates to variables. This step, this is something that's going to come into play more tomorrow, but it will come in a tiny bit today. So we need to make sure that this equation only involves variables whose rates we either know or we want. If we have any other variables in the equation where we don't know the rate and we don't want the rate, we have to get rid of that variable. So usually what happens is they give you enough information to write a second equation, and then you can substitute out the variable that you want to get rid of. Write it in terms of the other variables. So anyway, so that's that part. Then for all of these, you're going to differentiate with respect to time. And then you plug in your numbers and you solve. Today, we're doing what I would call baby-related rates. Okay? These will be like the G-rated related rates. Okay? Tomorrow, we'll do
R-rated.
Slight teenager related rates. PG, just PG. All right? So today we're doing infant child related rates. Tomorrow we'll get, tomorrow we'll get into PG. We will not do any PG-13 or R-rated related rates in this class. All right? If you want to get into the heavy duty related rates, that's what you can do in BC.
Oh, yay.
Okay? So we just stick with kind of the light related rates. All right?
That's nice.
Okay. There are a couple other things that you need to know. All right. All right, so other things to know. Kind of, some of these are just things to know, some of these are gotchas. All right, so number one thing that you need to know, if something is increasing, or in other words, getting bigger, its rate is positive. If it's getting smaller, then the rate is negative. We talk a lot about physical objects. So in this, for this unit, direction is irrelevant. We're only talking about, is that dimension or is the size of that object getting bigger or is it getting smaller? If it's getting bigger, it's going to have a positive rate of change. If it's getting smaller, it's going to have a negative rate of change. All right. All right. Thing to know number 2. Let's see. Oh, this is kind of a gotcha. Don't forget to use product rule when you need to use product rule. All right. There's a lot of differentiation in these problems. And by the way, all the differentiation will be implicit. And product rule is involved in many of them. So please don't forget product rule. Let's see, gotcha number 3. Don't forget units. If they ask for units, you have to give them units. Now, if they don't ask for units, you don't have to give units. It only will say, if the question says indicate units of measure, then you have to indicate units of measure. If the question doesn't, technically you don't have to. What you don't want to do is make up units. If they don't give you units, don't make up your own, all right? And don't put units. Just don't put any units, all right? Never use the word units. We don't put units per something, right? Just leave it blank. So the only time you ever put units is if they ask for it, but don't forget them, because usually the units are worth a point, right? So you can have a problem where it's, a 9-point problem, and the units are worth 1 of those 9. That's a big deal just for writing centimeters per second, right? So make sure you don't forget your units. All right, and the last thing, and this is a big gotcha, and this is a mistake that happens more often than anything else. Don't plug numbers into the original equation for things that are not constant. If something is a changing value, then you can't plug a number in for it in the beginning because it's changing. If you plug a number into an equation in the beginning and then take the derivative of a constant, you're going to get 0. You're implying that the rate of change is 0 when there is a rate of change. So you can't plug numbers in until after you take the derivative. Then you can plug your numbers in and calculate your rates. But you never plug numbers in prior to differentiating, unless it really is something that's static, that never ever changes. And you'll know, it'll help you when you draw pictures and stuff, you'll see. All right, are there any questions? Well, I'm sure you have tons, but probably half of you don't even know really what we're doing, right? So that's okay. Do y'all have this down? Okay. So, first example. The sides of a square are increasing at a rate of 5 centimeters per minute. Make sure this is getting on film. I'm going to move the camera over. Okay. Perfect. Okay, so the sides of the square are increasing at a rate of 5 centimeters per minute. All right, how fast is the area increasing? When the sides are 15 centimeters long. Now, you're not required to draw a picture. It really doesn't help you that much, but you can draw a picture, right? And for people who are visual, sometimes the picture is the difference between getting the problem right and not getting it right. So if you're a visual person, go ahead and just draw a square, right? There's nothing wrong with drawing a square, it only takes a second. So there you go, you got a square. Now, they didn't tell us what variables to use. People can get very creative with their variable assignments in these problems. So much so that the AP exam has gotten into the habit of telling you what variables to use, because I think they get tired of trying to grade these problems with all the different choices for letters. Don't get too creative. I personally don't use S for side because it looks a lot like 5. So when I have a square, I just call the sides X. You can use whatever variable you want. If it doesn't assign them for you, you can use whatever you want. But I tend to be boring and just go with X, because X is a nice, easy variable to see. It doesn't look like any numbers. It's a good letter to use. Okay, so let's talk about what we are given. Well, there's a square, pretend that's a square, and the side lengths are X. Is there one thing you're given where you just know how to write it? It'd be really easy.
X equals 15.
X is 15. Everyone okay with that?
Mm-hmm.
Is that good? Good. Okay. Now we got to get into the calculus part. The sides of the square are increasing, so they're getting bigger. So this is a square that's getting bigger, right? So like maybe someone is like grabbed a corner and they've got a square drawn on the computer and they're making it bigger, right? Something like that. Someone the other day, the other year, sometime in the past couple of years, someone said, how about like it's like when the band makes a square on the football field and they all walk out, right? And just make a bigger square. No one can picture that. I think that's neat. Okay, so anyway, so here we go. So we have a square that's increasing at a rate of 5 centimeters per minute. So we need to figure out a way to write the rate of change of the side of the square. Now, you can let the units be your guide. We want to think about what variable is assigned that has a unit of centimeters, and then what variable is assigned or not assigned that has a unit of minutes. In this problem, what variable has a unit of centimeters? X. And we're talking about the rate of change of the sides, right? And the sides are measured by X. So this is X. Minutes. What letter would you like to use to represent minutes? T for time, right? We use T. You're always going to use T. Don't pick another letter for time. Just use T. All right. So the way that we'd write the rate of change of the side of the square using calculus notation.
Like dx over dt?
So dx dt is 5. This is the rate of change of the length of the side of the square with respect to time. Okay? Does everyone understand how we came up with dx dt? This is the hardest part. Once you get this concept, the problems will get much easier. All right, so the rate of change of x, the rate of change of the length of the side of the square, the rate of change of x with respect to t is 5. And let the units guide you. Think x is measured in centimeters, time is measured in minutes. Does that make sense? Okay. That's everything we're given. Now we need to write down what we're trying to find. We want to find how fast the area is increasing. Now what letter do you want to use for area? A. Okay. So in calculus notation, we want the rate of change of the area, how fast the area is increasing.
dA dt.
That's dA dt. I tend to use capital A for area. So dA dt is what we're trying to find. How's that sitting with you? Okay, we're not trying to find the area. If I said, hey, find the area of a square with a side length of 15, that's just, you're just back in geometry, right? Okay, we're not trying to find the area, we're trying to find the rate that the area is changing. Okay, so now we've written what we're given, and we've written what we're trying to find. Now we have to write an equation that relates the variables. Can anyone tell me an equation that relates, now not the t is never going to be in these equations, but we need an equation that relates a and x.
X times x, right?
Yeah, area equals x squared. Is everyone okay with that? It's a square, right? So you need an equation that relates the variables. It's usually going to be geometry. Not always, but often. So area equals x squared. All right, next thing you want to do, this next step, the step 4 that's a little confusing, you want to look at each letter in your equation and ask yourself if you know or want the rate for each letter. So for A, do we know or want this rate?
Mm-hmm.
Yes, we want this rate. Do we know or want dx dt?
Mm-hmm.
Yes, we know dx dt, so we're good. There are no letters here that don't have rates written over here. Does that make sense? Okay, so now we're good for number 4. Number 5, we differentiate with respect to t. Oh, how fun, it's implicit, right? I'll get you started. The derivative of a with respect to t is 1 dA dt. Everyone take a second and write the derivative of x squared with respect to t. It seems very dark. What's the derivative of x squared with respect to t? dx dt. Now we can plug in our numbers and solve. All right? If I plugged in my 15...
Mrs. Price, when it's convenient, could Jacob Lewis come to Suite 1320 for a minute?
Sure. Yeah, it'll be in about 10 minutes.
That's the discipline office. You're
Uh,
gonna get paddled.
All right. If we plug the 15 in here, all we get is that area is 225. That doesn't help us at all, right? Because first of all, the area, yes, it's when the sides are 15, the area is 225, but the sides are changing, right? So it's not like the area is a constant of 225, just at that moment it's 225. And what we're saying here, let's go ahead and plug in our numbers now. So when x is 15, so we get 2 times 15, what's dx dt? 5 times 5, so we get 30 times 5, which is 150. And by the way, for units, it would be the units of area over the units of time. We want, this is dA dt, so what would be the units for area?
Centimeters.
Centimeters squared.
Square, that's all, man.
And what are the units for time? Minutes. So what this is saying is at the moment when the sides have a length of 15 centimeters, the area is changing at a rate of 150 centimeters squared per minute. Now, even though the side lengths change at a constant rate, the area changes at a variable rate. So it's dependent on the size of the square at that particular moment in time. If the sides were 20, you'd end up with 2 times 20 times 5, right? So you'd end up with a rate of 400 centimeters squared per minute. So the rate is actually increasing. But the rate is dependent on both the side of the square and the rate of change of the size of the square. So there's 2 inputs for your rate of change for your area. All right, so do you kind of get a feel for how this works? Okay, that was a really nice, cute, simple problem. That was an infant related rates.
Unrated.
It's an unrated. All right. So now we're going to get into a slightly more
Like Princess in the.
complicated one. So now this will be like
That's what it was.
elementary school related rates.
Can we just use movies as reference?
We're going to do grammar rates, right? Grammar school related rates.
So kind of like the Fox and the Hound.
Fox and the Hound, yes. Yes.
Would be the movie equivalent.
That would be our analogy, yes. Okay. Alright, so here's our next example. It wouldn't be related rates if we didn't have a ladder leaning against a wall. Alright, so we have a 25-foot ladder. It's leaning against a vertical wall. I'm gonna move this out just a tiny bit so it all gets in. There. Okay, of course someone's pulling the bottom away. The bottom of
Could be
the
Wile E.
ladder.
Coyote.
Huh?
That could be the fox.
That could be the fox. The hound is up on the ladder.
Yeah.
The bottom of the ladder is being pulled away. At a rate of 3 feet per second. So he's really moving it. Part A. How fast is the top of the ladder moving when the bottom is 15 feet from the wall? Part B. Yep. How fast is the area of the triangle formed by the wall, ground, and ladder changing when the bottom is 15 feet from the wall? Okay, a lot of writing, but it's okay.
I don't think these animals are smart enough. They're just foxes in hell.
I'm sure you can step it up with this problem.
Yeah, there's a lot more words.
Yes.
I'm going to draw this picture in a very specific way intentionally. So, everyone in copying, need 1 more minute. Okay. I'm going to draw the wall this way and the ladder like that.
Whoa. That freaks me out. Draw it.
Now, I ask you to have mercy on your calculus teacher, and please don't label horizontal dimensions y and vertical dimensions x. All right? Horizontal x, vertical y. Okay? Just stick with that. We're all going to stick with that convention. We're going to be conformists, because otherwise what'll happen is I'll start grading your paper and I'll start taking off points, and then all of a sudden I'll realize that you switched your variables, and then I have to cross off all my red ink, and it just gets messy, right? So horizontal dimensions, please use x. Vertical dimensions, please use y. And then if there's a diagonal dimension, use z, right? X, y, z, or a, b, c. Okay. Probably what I'll do is on this next test is I'll just name the variables for you. All right, so here we go. We've got our triangle x, y, z. Now, first thing we have to do is we have to write what we're given. So someone tell me something that we're given.
13, 25, 25 feet matter.
Z is 25.
15.
Z is 25. Okay. Alright, yes, we have a 25-foot ladder, Z is 25. Good. Something else that we're given.
DX GT was 3.
That is perfect. That's exactly right. dx dt is 3. Now, the ladder is going that way, which means that this point right here is moving to the left. Does that change? Should I write the rate -3?
No,
No,
Why not?
because
He
it's
said-
still increasing.
Because x is getting bigger, right? If the thing that you're talking about is getting bigger, it's a positive rate. If it's getting smaller, it's a negative rate. All right? Okay. Doesn't matter about direction, it's just, is it getting bigger, is it getting smaller? Good. And then in part A, is there anything else that's given?
X is 15.
X is 15, right? All right, so now we've written what we're given. Now we need to write what we're trying to find. In part A, how fast is the top of the ladder moving? So here's the top of the ladder. I'm just going to make a fairly safe assumption and say it's going that way, right? You don't have to, but it's moving. I think it's pretty safe to know that it's going down. So what would represent the rate of change that the top of the ladder is falling?
dy dt.
dy dt. Because the rate that this dot is moving is the same as the rate that this dimension is changing. There's kind of a, and that's something that's a small point to understand, is that sometimes they'll ask you, like, how fast is this person running? When you're not trying to time the actual person, you're just measuring how fast that dimension is changing, right? It's the same kind of thing here. How fast is this point moving? It's the same as the rate that this dimension is changing. All right, so we're looking for dy dt. We need an equation that relates these variables.
1/2 BH. Is that
1/2 base times height, that would equal
the area?
area.
My bad.
That's really throwing some extra stuff in, that might be tricky. I'll give you a hint.
A squared plus b squared equals c squared.
Yes, yeah. A lot of triangle problems use Pythagorean theorem. Yeah, that's kind of a safe fallback for triangle problems, right? So, for this triangle, lovely right triangle, what squared plus what squared equals what squared?
X squared plus y squared equals c squared.
Alright, so here we go. We have an equation, it relates our variables. Now we're going to check and make sure we either know or want all the rates. Do we know or want dx dt?
Yeah.
Yes.
Yeah, we know dx dt, it's right there. Do we know or want dy dt?
Yes.
Yes, we want dy dt, it's right there. Do we know or want dz dt?
No.
No. We don't know it, we don't want to know it.
But isn't it
Z
always-
has to go.
We know.
Isn't it always 25?
Yes. So good. Okay. Guys, did you all hear Eleanor? She said, but isn't Z always 25? Yes. Z is a constant. Z is never ever changing. It's the length of the ladder, unless it's like one of those collapsible ladders and it collapses as you're moving, right? But let's just not go there. So let's just say it's one solid ladder that is 25 feet. Then you can kill the Z and write this instead, and it'd be absolutely correct. As a matter of fact, sometimes when I have things that are constant and they're truly constant, never ever changing, I don't even give them a variable name. Sometimes I'll just write the constant on the picture. Right? And then I don't have to worry about accidentally assigning a variable to something that's constant. See what I'm saying? Okay. All right. So I want you guys to take a second and differentiate this with respect to t. Everyone got it? I see some good and some with issues.
Shots fired.
What's the derivative of x squared?
2x dx dt.
Good. 2x dx dt. Everyone get that?
Yeah.
What's the derivative of y squared? 2y dy dt. What's the derivative of 25 squared?
0.
It's 0. It's not 2 times 25 d25 dt?
No.
What would the rate of change of the number 25 be?
0.
It's a joke. 0, right? Because it's just 25, it doesn't change, right?
So
Okay,
funny.
yeah. So the rate, if you gave it a variable name of z and did 2z dz dt, then, which students do from time to time, they accidentally go ahead and throw a rate down for something that's constant, then you can think to yourself, well, dz dt, that's the rate of change of this side. This side's never changing, so its rate of change is 0, right? So, and then you just plug in your 0 and you're still okay. So, even if you left the z and accidentally differentiated it, you should still, when you plug in, you should still get a 0, right? Because it doesn't change. All right, do you all understand this? Okay, and then you can kill the 2's if you want to divide both sides by 2. Once you differentiate, that's when you can plug in. So for this problem, x is what?
3 times 15.
What's x?
15.
15. And then dx dt is
3.
3. Uh-oh. We don't know why.
Pythagorean theorem.
Ooh. And then dy dt is what we're trying to find. So just write dy dt equals 0. So we need a number for y. If I have an x and I want to know y, let's say it was any problem, even like on your last test, where do I go?
Plug it back into the original.
Original function, right? Because that's what relates x and y. So if you have one of them and you need one of the other variables, look at that original function. So this one. So we have x is 15. We have 15 squared plus y squared equals 25 squared. Does anyone recognize and just know what y has to be?
12. I have no idea. 18, 15, 20,
Oh, it's
23,
in 3, 4,
13,
5.
26. That's what I was going to say. Oh, funny.
Okay. All right. It's a what multiple? This is a 3, 4, 5 multiple, right? If you recognize this is 5 times 3 and this is 5 times 5, this has to be 5 times 4. 3 times 5, 4 times 5, 5 times 5. They will often, because there's usually no calculator, you will often get Pythagorean triples. So it's helpful if you know your 3, 4, 5, right? And it's all its multiples, right? 6, 8, 10, right? All of those. If you know your 5, 12,
13,
13, right? Anyone know 8?
14. I have no idea.
19.
16, 17. That's...
How are you doing?
Wait, okay, that's definitely not one.
41.
That never comes up. I bet. Like,
It comes up all the time.
What are you
That
doing?
doesn't.
Yeah. And I think there's one 7, 24, 25.
Yeah, I think.
7, 24, 25?
Before you go to bed.
I would have to check that to make sure. Right. So anyway, these, I will tell you right now, these 3 come up all the time. All the time. These don't come up very often.
That's what I was saying.
Okay. So anyway, all right, so here's what we get. We get 45 plus 20 dy dt equals 0. So dy dt equals, you subtract the 45 and divide by 20, and then you can reduce and get negative 9, that's a 9 fourths. We need units for dy dt. What is y measured in? Feet. What is time measured in?
Seconds.
Seconds. How's that? That okay?
That's perfect.
Good. That's part A. Okay, now we gotta do part B. We got lots of time. Alright, part B. How fast is the area of the triangle formed by the wall, ground, and ladder changing when the bottom is 15 feet from the wall? We've already written everything that we're given. We need a letter to represent area. What do you want to use?
A.
A. So what are we trying to find for part B?
D-A-D-T.
dAdt. How fast is the area changing, right? So for part B, we're looking for dAdt.
Sorry, bro.
See if you can come up with a formula that relates the variables. One of you came up with it about 5 minutes ago.
1/2 piece BH.
Okay, except use these variables.
Alright, well, that's gonna make it so much harder. 1/2 x, y.
Yeah. Did you guys all see how he got that?
No.
Area of a, okay, good. Area of a triangle is 1/2 base times height. So area is 1/2 xy. Do we know or want dA dt?
No.
Yes, we want.
Yes,
Oh,
we
yeah.
want it. Do we know or want dx dt?
Yes.
Yes. Do we know or want dy dt?
Yeah.
Yes, we know dy dt, we just found it, right? Yay, it's a good thing. Okay, so guys, haha, differentiate that with respect to time. What rule are you gonna have to use? Product rule.
Oh, no, we're not.
Yes,
We're
you
just gonna
are.
mess up and then you're gonna write it up.
That's probably
Oh
very
no,
true.
that's
No, give it a try. At least try.
Give this swirl.
Do this. Do this. There is no learning from sitting and watching. There is only learning from
Give it a
doing. You have to
swirl.
do it.
This one.
You did the JP cruise. Look at your picture. Hold your pants.
Mustafa, this is all going on tape. You know this, right?
Give it a swirl. I'm gonna rewatch this like every night.
Oh, weird. F primary G minus F G prime.
No, it's not minus, it's plus. It's a product rule, come on.
It's been 4 days. So wait, something raised to the 0 is 1. That's right.
It's raised to the 1, so it's 1. It's really not that.
No.
Yes, he does.
Yeah. Yes.
Oh,
So, but
that's
it's-
Alright, so what I do, when I have a one shot in front,
Oh, you have to put it on.
I kind of link it with whatever the first letter is. So here's like 1/2 x times y.
Oh, it broke.
So the derivative of 1/2 x is
Alright, see, I was doing that wrong.
times so it's not
No,
different
it's
with
just
respect to
like
t,
7 above.
so it's
So what'd you
1/2, what's the derivative of x?
I got a 9, it was. Because
Times y.
Is that what you got?
Plus 1/2 x is the derivative of y.
0 x plus y. What'd you get, Jim?
What done here yourself, man?
But we're not writing, we're not
Some
computing.
worry
it
about
yet.
you
We're just
in a
writing.
swirl.
What's the derivative of
Like you.
I got it.
Right. I'll walk through
Oh,
here.
shit.
Alright, guys. When I have to do this and there's a coefficient, I kind of group the coefficient with the first letter. You don't have to, you can distribute it at the end, but I do that. So what's the derivative of a with respect to t? Good, dA dt. You all should be okay with that. Product rule. F prime g plus fg prime, right? Okay.